All right. Good morning again, everyone. So today we'll continue our discussion with approximation techniques or polynomial approximation techniques. So we are still we are at module 5, medyo 1 week behind tayo. Pero that's fine. We are because we have a buffer, 1 week of buffer. Kaya lang sana yung break natin next week ay gagamitin na rin natin to start module 6 para hindi tayo kulangin sa dulo. Right, so this will be about curve fitting, and we will present and address some of the problems with interpolation. We'll mention what ano pa yung problema niya aside from the Runge phenomenon that we have encountered last time. So we'll be doing it until the 22nd, so ngayong week na to. And then we have lab exer 2 here, which would be on, or which will be due on the 25th. So in-adjust ko na siya ng isang week. So the objective for this module is to find the best polynomial fit to a given set of data. And instead na ibigay ko lang sa inyo yung formula kung paano hanapin yung best polynomial fit. We will derive formulas for this best fit. So at least i-present ko paano dinerive yung paggamit ng or yung pagkuha ng linear fit and quadratic fit. Tapos hopefully this will give you an idea on how to use or how to derive formulas for, say, a cubic fit or a quartic fit or kahit nga logarithmic or exponential fit. Pwede yung sundan yung derivation na gagawin ko today para yun yung gagawin, para yun yung pattern yung pag-derive ng formula for the general case. And if you want to see some more materials about it, I based my discussion here from this book, Elementary Numerical Analysis by Atkinson. So meron din siyang additional examples from there. Okay, but before that, since matatapos natin ngayong week yung Unit 1, I think we can have the first problem set. And in the other class, I proposed October 27 until November 1. So there would be a total of 4 to 5 problems, and the problem will or the problems will go live in Canvas on the 27th. And then ang submission niya ay sa November 1. So that will give you 1, 2, 3, 4, 5, 6. 6 full days to work on the problems. Though yun nga lang kasama niya yung weekend at saka yung November 1. Okay? Tapos ngayon ko lang na-realize, ngayon lang pagbukas ko nitong module, yung ko lang naalala na meron nga pala akong mga estudyante in both 174 and 155. Baka mag-overlap yung problem sets. Tama nga ba, Denmark? Si Denmark yung naalala kong student ko both them. What do you think? Okay lang ba itong schedule na to, or do you want to do it after the reading break? Though na-set ko na to dun sa kabilang section, though, what do you think? Gusto niyo ba i-move na natin after the reading break or tuloy na natin para wala na kayong problema before the reading break? Okay, so wala kayong reaction. So kung hindi kayo mag-react, itutuloy na natin to. Okay, so the idea here is 4 to 5 problems siya. Titingnan ko yung objectives ng bawat module. Tapos kung hindi na-test dun sa mga lab exercises, isasama ko siya sa problem set. So basically, expect one item to be, or 1 or 2 items to be more of an exposition. And then the other problems would be, kasi dun sa lab exercise, nakita ko, nagpa-derive na rin yung mga lab instructors nyo, nagpa-prove na rin ng some things. So, kung natanong na sa lab exercise, hindi ko na uli ipapagawa. Pero you might want to keep the programs that you use in the lab exercise because I think they will be useful for the problem set. Okay? So, halimbawa, yung ginamit niya sa polynomial interpolation or yung ginagamit niya sa splines, i-keep niyo siya kasi malamang kakailanganin niyo yung isa or dalawa sa kanila or at most tatlo sa kanila in order for the problem set. Okay? So, wala na akong option na in November 1 na yung latest na pwede ako magpa-submit. Kasi start na ng reading break on the 2nd. So para hindi ako ma-technical na kasi bawal magpa-submit ng kahit ano during the reading break. So let's set it to November 1. Or paano ko ba? Sige, pwede kong extend hanggang 11:59 p.m. para may ilang oras pa kayo para gumawa. And then siguro ibigay ko na rin ng November 6, ng October 26, Tuesday, para meron kayong isa pang additional day. So you'll have 7 days to finish it, 7 full days. So lang po may mga klase kayo in between. Pero 4 to 5 problems lang naman. I'll try to keep it into to 4 problems. So isa sa interpolation, isa sa algebraic interpolating polynomial, isa sa splines, ano pa ba? Isa sa norm optimized optimization, saka isa sa curve fit. Yun nga ba yung topics natin? So, basta, I'll try to keep it 4 problems. Pag hindi ko talaga kinaya ng 4 problems, gagawin kong 5. Pero, yeah, I'll try to minimize it as much as possible. Pero, yun. Okay, so wala kayong violent reaction about this. Ito na yung time yung makipag-haggle kasi after nito, hindi na natin to i-move. All right, so thank you. Mukhang agree naman kayo. Okay, so let's try to go here. So let's start our discussion about least squares curve fitting. So ang ginawa natin so far sa 174, in-address natin yung isang common problem that arise in application areas. Na yung data na nakukuha natin ay given as a discrete set of points, be it coming from observation of natural phenomena or galing siya sa experimentation or survey. Ang problema with the discrete set of data, hindi natin ma-apply kagad yung mga natutunan natin sa calculus courses. Kasi sa calculus courses, para makapag-optimize ng function, para makapag-analyze, para makita kung increasing or decreasing yung isang function, or to do anything about these functions, kailangan given yung function f. Usually, we want the function f to be continuous or differentiable, and sometimes also integrable. So, yun yung problema, na hindi talaga direct function yung nakukuha natin from real-life applications, more of discrete data, or pwede rin namang meron tayong function na makuha that models this phenomena, pero komplikado masyado yung function f, which might not be apt for machine implementation, right? So kaya natin tiningnan ano yung iba't ibang ways para makapag-approximate ng set of data or ng complicated function using some finite information about them, right? So kaya tinignan natin yung unang klase ng approximation, which is interpolation. And interpolation, the distinguishing property that sets it apart from other approximation techniques is that dapat sa interpolation dadaan yung function na pang-approximate natin dun sa given set of data. So we require 0 errors at the given data points. Now, everything went well kasi parang ang kinonsider natin ay polynomial interpolation. Pag meron kang n+1 points, magkakaroon ka ng degree or at most degree n interpolating polynomial. And we also look at the error term involved with it. At nakita natin na, pwede nating mapaganda yung approximation, mapababa yung error by either choosing the exabytes wisely. We can use the Chebyshev nodes or the Legendre nodes to minimize the L infinity and the L2 norm respectively of the error term. Or kung wala tayong degree of freedom to choose or wala tayong freedom to choose the interpolatory abscissas, tiningnan natin, pwede ko sigurong paramihin yung number of points na ginagamit natin. However, there's a drawback to using a large number of points because a large number of points will give rise possibly to a polynomial of a very large degree. All right? Tapos nakita natin may problema pag malaki masyado yung degree ng interpolating polynomial. Maaring maging subject tayo sa Runge phenomenon, which is basically the presence of wild oscillations or wiggles in the polynomial or in the approximating function near the endpoints of the interpolatory interval. Isa siyang problema ng interpolation. So ang naging remedy natin sa Runge phenomenon para ma-avoid yung Runge phenomenon ay mag-paste together or magdugsong-dugsong ng polynomials of small degrees between two consecutive abscissas, right? So consider natin yung piecewise linear interpolants, which is we pasted together linear functions connecting two data points, or we also considered cubic splines, wherein nagko-connect tayo ng mga degree 3 polynomials sa mga subintervals. Okay? Which seems to be fair and a nice remedy to the Runge phenomenon. Kaya lang ang problema, pag marami kang points na, pag marami kang data points, so ibig sabihin komplikado yung pag-derive ng cubic splines sa piecewise linear interpolants kasi marami kang hinahanap na parameters. Okay? Now, we'll motivate the use of another technique, and this is called least-squares curve fitting. This is an example of a curve fitting algorithm or method, and this one is a generic kind of approximation. Hindi na siya katulad ng interpolation na magre-require ng zero error dun sa nodes. So, makakita tayo dito ng mga approximating functions na hindi mismo dumaraan dun sa given set of data, but instead we want to minimize the error from the given data. So hindi natin i-require na dadaan siya dun sa data points. Well, you might think this is disadvantageous, pero medyo advantageous to because we will be treating the error in a global manner. Sa interpolation, ang nire-require lang natin ay zero errors dun sa data points, right? Wala tayong pakialam dun sa ibang points na sa pagitan ng mga abscissas. Nadadamay lang sila dun sa kagandahan ng interpolation. And as a consequence of that, hindi natin nagagamit yung interpolating polynomials para i-approximate yung function value sa labas ng interpolatory interval. Remember, kung ang interpolating interval natin ay closed interval AB lamang, so yung interpolating polynomial ay valid lamang sa loob ng closed interval AB. So kung gusto nating i-approximate yung f of c, okay, for some number c, dapat si c ay nasa loob ng closed interval AB para magamit natin yung interpolating polynomial para ma-approximate si f of c, right? So provided c is in the closed interval AB. Outside of the interpolatory interval, hindi natin pwedeng gamitin yung interpolating polynomial. So you can think of restricted yung domain ng interpolating polynomial sa closed interval AB. Kasi nga by design, local yung treatment ng error. Sa curve fitting, global yung treatment ng error. So in a sense, parang ang mangyayari ay pwede natin siyang gamitin para sa forecasting. So kung ang smallest node mo ay A, ang biggest abscissa mo ay B, hindi ka nalilimit dun sa closed interval AB. Alright? So pwede mong gamitin yung curve fit in order to extrapolate or to approximate a value beyond the interpolatory interval. So halimbawa, you're trying to approximate the value of your stocks, say sa day 367, pwede mong gamitin yung data from day 1 until day 365 kung gumawa ng curve fit para ma-approximate yung para sa day 367. Sa interpolating polynomial, hindi mo pwedeng i-substitute yung day 367 kung ang interpolatory abscissas mo ay between 1 and 365 lang. Okay. Now, it's not just that. Medyo mayroon pang mas magandang ina-address itong curve fitting, namely yung instability ng interpolating polynomial with respect to perturbations in the input data. When we say perturbations to the input data, ito ay yung lalagyan lang natin ng konting error o konting noise yung data na gagamitin natin para buuin yung interpolating polynomial. So, yung mga f of x sabay na gagamitin natin dun sa Lagrange form or dun sa cubic spline or dun sa piecewise linear interpolant, isipin natin na siya ay mapaperturb or subject to measurement noise or to simulation noise or to round off error. Ibig sabihin, dun sa data na gagamitin natin, hindi eksakto yung mga yung mga function values. Posibleng contaminated sila ng maliliit na errors. Right? So we say an algorithm or a method is stable. So stable siya kapag yung maliliit na perturbations result to small changes in the output. Tapos unstable siya kapag maliliit na changes dun sa input data brought about big and often significant changes in the output. So which makes sense kasi kung maliit lang yung pagbabago dun sa input data, dapat konti lang din yung mabago sa output. And we want those are the ideal methods that we want to keep insofar as applications is concerned. Kasi halimbawa nasa lab ka, nagko-collect ka ng data. So halimbawa sa tungsten emittance. So isa-subject mo yung tungsten to some temperature, tapos titingnan mo kung ano yung emittance at that particular temperature. And of course, dahil finite naman yung mga measuring devices natin, kapag continuous yung data o yung type of data na in-expect mong gamitin, hindi natin mapipinpoint ano yung eksaktong value ng emittance at a temperature. So pwede nating sabihin, this is accurate, say, up to 5%. Kasi yung measurement natin ay flawed to be, is designed not to be perfect. Or halimbawa, bibili ka sa palengke ng 1 yarda ng tela. So hindi natin masasabi na yung makukuha nating tela talaga ay 1 yarda. So kung gagamitin ko siya dun sa data ko, hindi ko sure na 1 yard talaga yung kailangan kong ilagay dun sa algorithm natin. Kasi nga, finite yung ruler na ginamit possibly dun sa tindahan. Hindi natin makukuha yung exact data, but we expect to be the data to be subject to small measurement or to measurement noise or to round-off errors. Lalo na halimbawa, simulated yung data na ginagamit mo. I mean, yung data na ginagamit mo ay product din ng isang numerical simulation. So kung halimbawa irrational yung makukuha mong function value out of your simulation, hindi mo mapapass on yung exactong value papunta dun sa bago mong algorithm, dun sa interpolating polynomial mo, for instance. Kasi nga, meron niyang maliit na error from the actual values. And we will illustrate in the next few slides na unstable yung polynomial interpolation using equally spaced data. All right? So and we'll do that by considering the function capital F, which is sine of 2 pi x, over the interval -1 to 1. And we will try to interpolate it using 21 equally spaced points. And it will be, 22 equally spaced points. And if we're going to use 22 equally spaced points, then we will have a degree 21 interpolating polynomial. Right? So kung gagawin natin yon, so i-assume ko na perfect yung computing device ko, yung pang-compute ko ng f of x. Right? So kung perfect siya, ito yung makukuha kong interpolating polynomial. Okay? So sa figure A, pinapakita dyan yung graph ni capital F, which is the function to be approximated, and little f, which is the degree 21 algebraic interpolating polynomial obtained using the 22 equally spaced data points. And you will see that little f and capital F almost coincided with each other all throughout the interpolatory interval -1 to 1. Kasi nga, isang kulay lang yung nakikita ko sa graph, where in fact, I'm expecting 2. So the reason behind that, medyo nag-overlap na yung graph nila to some extent na kahit visually or a visual inspection will not reveal the changes or the difference between them. And we're sure na interpolating functions sa little f kasi dumaan siya dun sa mga data points represented by the orange circles. All right? So everything is fine. Kahit degree 21, hindi naging subject sa Runge phenomenon yung interpolation natin. And everything seems to work well, right? And true enough, if you plot the absolute error, so this is the function e of x, which is the absolute value of capital F minus little f. So pag ginraph natin to, makikita natin na yung absolute error ay at most 10 to the -8, right? Kasi 10 times 10 to the -9 na siya. So pagpalagay na natin, round up na natin, siya around the 10 to the -8. And an absolute error of 10 to the -8 is small enough kasi Ang magnitude naman ng function values na ina-approximate natin ay between 0 and 1 lamang. So this guy seems to just have, or to induce what? 10 to the negative 6% error, which is pretty good, right? So everything worked well. Walang Runge phenomenon, walang unexpected anomalies happening, right? Pero ito yung problem sa polynomial interpolation using equally spaced data. So pag binago ko lang ng konti yung mga interpolatory abscissas, there's a chance na ibang-iba yung makukuha ko na interpolating polynomial. So what I did in the next experiment is, okay, itry ko kaya na i-assume na yung data points ay contaminated by noise of order 10 to the negative 3. So makita nyo sa figure A, yung original data points saka yung perturbed data points. Though, so yung original, siya yung blue circles, yung orange crosses, sila yung perturbed data points. So makikita nyo, konting-konti lang. Inisod ko lang siya ng counting-counting. And how did I get this perturbed data points? Ginamit ko itong formula na to. Alright? So, ito yung function value kay capital F, f of x sub I, right? The actual function value. Minsan tinatawag ko itong yi din. Alright? Kaya lang dahil transcendental itong value na to, halimbawa gumamit ako ng calculator para makuha itong data na to, hindi ko maka-capture yung eksaktong value ni sine 2 pi xi. Or kung galing siya sa experiment, posibleng contaminated siya by measurement noise. Right? So hindi ito yung eksaktong number na usually mai-input ko sa interpolation algorithm ko. Instead, what I'll get is a y tilde. Yung mga y tilde, sila yung mga function values, pero meron silang additional term dito, which is, you can think of it as the noise, possibly due to simulation error or to round-off error or measurement error, right? So, meron akong random number r sub I between negative 1 to 1 at saka imumultiply ko siya ng noise magnitude level na 10 to the negative 3. So that itong multiply ko rito ay almost 10 to the negative 4, right? Because this is less than 1 times 10 to the negative 3. So this is about order 10 to the minus 4, which is small compared dun sa magnitude ng sine pi x. So kasi ito ay magnitude 1, ito ay order 10 to the negative 4, or you can say 10 to the minus 3 as well. So 2 orders lower than the actual function value. So mukhang maliit lang talaga yung epekto nitong added noise. And true enough, if we look at the graphs of the scatter plots of the original and the perturbed data points, makikita nyo, konti lang talaga yung inison. All right? And if the algorithm is stable, ibig sabihin yung pagkang ginamit ko dun sa interpolation ay yung perturbed data points, dapat konti lang din yung change. Which makes sense kasi halos magkalapit lang naman yung function, magkalapit lang naman yung perturbed saka original data points. So, ibig sabihin, pag gumawa ko ng interpolating polynomial, dapat halos ganito lang din yung itsura. Dapat hindi sila maglalayo from each other, right? Kasi nga yung interpolation, dadaan ka dun sa eksaktong data points, right? And if you're not convinced na maliit lang talaga yung perturbation, pwede mong ipa-plot yung absolute error. So this is the difference between y, or the absolute difference between y sub I, the actual function value, minus the perturbed data points, or the perturbed function values y tilde. And you will see that indeed they are of order 10 to the negative 3 talaga. Okay? So maliit lang talaga yung na-introduce na error by adding a Gaussian noise, or a normally distributed random number times the magnitude 10 to the minus 3. Tapos para makita yon, sige, gamitin ko nga yung perturbed data points para kumuha ng degree 21 interpolating polynomial. And we are hoping that the polynomial that we'll get using the perturbed data points will be close to the interpolating polynomial that we got using the original data points. So, however, hindi yun yung mangyayari, as you will see in figure 5.3. Sa figure 5.3, makikita natin yung overlapping graphs nung little f. Si little f, ito yung una nating nakuha ang interpolating polynomial using the actual data or the original data points. Tapos si g, represented by the orange line, siya yung nakuha natin using the perturbed data, right? You'll see that they both interpolate their respective data sets kasi nagpa-pass through yung graphs dun sa mga data points na ginamit. Okay? However, makikita natin na kahit magkalapit yung original data points at saka yung perturbed data points, visually striking yung difference sa pagitan ni F at saka ni G, especially near the edges of the interpolatory interval. So dito, okay, halos nag-overlap sila, which is what we expected. However, there's a significant difference at the tail end of the interpolating or the interpolatory interval. Okay? So ito yung sinasabi natin na indication na unstable yung interpolation using equally spaced data points. Kasi nga, maisod lang ng konti yung data points na gagamitin mo. I mean, kahit konting-konti, katulad nung ginamit natin sa specific simulation na to, na bago significantly yung features ng interpolating polynomial. So this is one problem of interpolation using equally spaced points. May mga remedy, pwede kang gumamit ng Chebyshev at saka Legendre nodes kasi sila yung mas stable na gamitin instead of equally spaced data points. However, most of the times we want to look at other ways, right? And again, we want to hit two birds using one stone na ma-address natin yung instability ng polynomial interpolation as well as we can come up with an approximating function that can be used in order to forecast values. I mean, to approximate values beyond the interpolatory interval. And that's what curve fitting will provide us, right? Okay, so curve fitting is an example of polynomial approximation. Kaya, or approximation in general. Hindi siya katulad ng interpolation na magre-require na dadaan eksakto yung function, yung approximating function dun sa data points. What we wish to do is to minimize some measure of error. And in particular, if you're talking about least squares data fitting, we want to find the function among a set of candidate functions. So rito si S ay set of candidate functions. Ikaw yung nagsiset nan sa simula. Ano yung candidate functions na gusto kong gamitin dun sa approximation? Tapos usually ang ina-approximate ko ay discrete set of data. X sabay, Y sabay, as I goes from 1 to big N. Meron akong big N data points. So pipiliin ko yung function f hat mula sa class S dun sa mga candidate functions ko so that si f hat yung mag-minimize nito. So f hat is chosen to be the minimizer of this expression E among the class of functions S that we set earlier. Right? Ano ba yung CE? CE ay yung least squares error. Siya yung squared errors. So kung makikita nyo, si f of x ay siya yung function value dun sa mga candidate functions S minus the given y value from the data set. Square mo lang yung square mo lang yung difference nila and take the sum. And you will see that we are minimizing the sum. So sort of, we are treating error in a global fashion. Hindi katulad sa interpolation na ni-require natin na f of x I equals yi for all I from 1 to n plus 1. Kasi ni-require natin sa interpolation na 0 yung error dun sa mga interpolatory nodes. Dito sa curve fit, hindi natin nire-require na 0 yung errors dun sa mga y sabays, pero gusto natin yung sum ng squared errors ay maliit. So sort of it gives us a global flavor to the measure of error. Okay? So yun lang naman yung idea ng curve fitting. Meron kang given x sabay, y sabay. Tapos sa pagtingin mo dun sa data points, magkakaroon ka ng idea ano yung itsura ng graph posibleng graph ng function na daraan o malapit dun sa mga exabytes? What is the best fit to get to this given set of data? And I will postulate na, okay, posibleng isa siyang linear function, posibleng quadratic function siya, posibleng exponential, and so on. And I will put all of those functions into a set S of candidate functions. And I will choose from S, ano among them yung functions that will minimize the squared errors. All right. And we will talk about two types of class S, all right, na set of candidate functions. Namely, gagawin natin candidate functions lahat ng linear functions, tapos quadratic functions din. I-derive natin paano makuha yung minimizer f hat ni function E. Right? And then hopefully this will give you an idea how to do it in other cases like for powers x to the power n or para sa exponential or logarithmic fit. Okay? Let's probably start with the simplest case, which is the linear least squares approximation. And probably if you took a statistics course, medyo narinig nyo na to. Parang siya yung ginagamit sa linear regression, okay? Or sa linear forecasting. So, yeah. Nakita natin, paano nga ba dinerive yung formula doon? Again, we start with a given set of data, x sabay, comma, y sabay. Tapos usually yung ginagawa, gumagawa tayo ng scatter plot ng data points para makita natin approximately, at least visually, ano kaya yung klase ng function na mag-fit dun sa given data natin the most. And I will collect my guesses into a collection of candidate functions, and that's what we call script S, right? So halimbawa, pinlot mo yung x sabay, comma, y sabay sa isang scatter plot and you see na, parang naglalay sila sa isang straight line or malapit yung trend sa pagiging isang straight line. So if that is the case, then you can set S to be the set of all linear functions. And what we will do is we will choose among these linear functions sino yung nakakapag-minimize ng least squares error. So remember, the least squares error is actually the sum ng f of f hat x sub f of x sub I minus y sub I quantity squared. So ito yung i-minimize natin. So kung yung candidates natin ay mga linear functions, so si f hat, ang itsura niya ay mx plus b for some unknown m and unknown b, right? So yun yung hanapin nating parameters. Lahat ng elements ng set S natin, set of candidate functions, ay pwedeng masulat in this way. Kasi nga lahat sila linear functions lang. And then if I will use this form for f hat x sub I, so mapapalitan si f hat x sub I ng mx sub I plus b minus y sub I. And this is the sum of the squared errors, but now treated as a function of m and b. Kasi nga dito sa function na to or sa summation na to, ang hindi natin alam kung ano yung value nila ay si m at saka si b. Right? So because we know the x sub i's, we know the y sub i's, so what's left to be determined would be the m and the b's. And we will choose m and b so that this guy is minimized. And then paano nga ba mag-minimize ng function of two variables? Kasi si E ngayon ay function ng variables m and b, right? So kung matatanda niyo sa multivariate calculus niyo, I think it's math 38, ang necessary condition para ma-optimize or ma-minimize ang isang function ay mag-zero yung partial derivatives, right? Or kung maalala nyo, kahit sa math 36, nag-occur ang minimum sa isang point kung saan ang tangent line ay horizontal, right? E ang slope ng tangent line ay yung value ng derivative. So that also extends naturally to the case of multivariate function, wherein we just need to set the partial derivatives of E to 0. And whatever points M and B satisfies that equation, then they are the critical numbers, meaning sila yung mga candidates para magbigay ng minimizer ni function E. Alright? Kaya siya necessary condition. Kasi kung siya yung minimizer, dapat mag-zero yung partial derivative sa kanya. Alright? So we'll use that fact. So that means kung minimizer si B, M, or parang dapat m comma b to. But not a big deal, right? Dapat yung partial ni E with respect to M at saka yung partial ni E with respect to B parehas equal kay 0. Alright? Now, let's compute the partial of E with respect to M. So, balik tayo dito. So, it is something squared or sum ng something squared. So, ang derivative niya ay sum ng something ng 2 times something. Tama? Alright? So, bababa yung power 2 in front of the base. Raised to the power 1. Then chain rule will kick in. We'll need to multiply what we got so far by the derivative of the base. Anong derivative nito with respect to m? Now, everything without an m will be treated as a constant. So the y sub i's are constant. B must be treated as a constant. Derivative ni mxi with respect to m ay equal lamang kay xi. So may multiplier to na xi. And that's what we got here. So this guy is direct computation of the partial derivative of E with respect to M. And then I can take the constant 2 out of the summation. So that ko siya sa harap. And then I can divide both sides by 2 to arrive at this equation. Right? Or I can use properties of summation to write this as the sum ng x sub I squared times M plus sum ng x sub I times B equals sum ng y sub i's. Right? So konting algebraic manipulation lang nito will give us this. Because remember, we know the x sub i's, so we can compute this summation. We know the x sub i's, we can compute their sum. We know the y sub i's, we know their sum. The only unknowns here in this equation would be m and b. So a necessary condition for MB to be a minimizer ay ito dapat totoo. Right? Similarly, the partial with respect to E, the partial of E with respect to B rather, must be equal to 0. So computing ko tong partial na to. If I do that, same thing. Ito ay bababa in front of the base times chain rule will kick in. Let's multiply what we got so far by the derivative of the base. Pero anong derivative nito with respect to B? Everything without the B will be treated as a constant. So mxi will have 0 derivative. Y sub I will have 0 derivative. Derivative ni B with respect to B ay equal kay 1. And that's why ito yung makukuha yung partial with respect to B. And again, I can divide both sides of this equation by 2. I get this guy. And then simple manipulation using properties of summation will lead us to this. Right? Now, equation 5.6, this guy, and 5.7 are the necessary conditions para dun sa minimizer. Okay? And I will just put them together into a linear system given by equation 5.8. So ito yung linear system na gusto nating isolve for M and B. Though medyo intimidating siyang tingnan, hindi naman siya mahirap kasi two equations lang siya, dalawa lang yung unknowns, si M at saka si B. Right? Kasi lahat ng mga factors dyan, kaya nating makompute from the given set of data. Right? So si M at saka si B nga lang yung hindi natin alam. And you can solve this using your usual elimination or substitution or Cramer's rule. Right? Pero titingnan natin, ano nga ba or ilan ba yung solutions nito? Kasi kung maraming solutions, kailangan pa natin i-compare yung function values nila or gumamit ng second derivative test para ma-check kung sino yung magbibigay ng local maxima or local minima. Alright? Pero kung isusulat ko to in matrix form, ganito yung magiging itsura ng equation, ng system 5.8. And we know that the system in matrix form will have a unique solution whenever the determinant of the coefficient matrix is not equal to 0. Right? Kakaroon tayo ng unique solution kapag ang determinant nito ay hindi equal kay 0. Pero ang determinant nito, if you remember, product na pababa minus product ng pataas. So ito yung determinant ng coefficient matrix. And this guy will be equal to 0 if and only if yung mga x sub i's are equal sa isa't isa. Hindi na natin siya i-prove, pero that's the only way that equation 5.10 will hold. Kapag yung mga exabytes ay lahat equal to each other. So if we will impose na dapat iba-iba yung exabytes natin, then we are assured that equation 5.9 or system 5.8 will have a unique solution. At dahil unique lang yung solution niya, isa lamang yung candidate natin para sa minimizer. At yon yung M, B na makakasatisfy ng system na to. Dahil siya lang yung critical number, siya na dapat yung minimizer. Alright? So, yun yung kailangan natin gawin. So, isolve itong system na to, makukuha natin yung M and B that will minimize the squared errors or the sum of the squared errors. Okay? And as I mentioned, hindi naman ganon kahirap isolve tong system na to kasi 2 by 2 lang siya. Pwede nyo nga siyang gawin by hand kahit hindi nyo na siya i-program, or pwedeng sa program nyo tawagin itong AX equals B, right? Kaya lang 2 by 2 nga lang siya. So si X ay A inverse B lang. So si X siya yung naglalaman ng M at saka B. Right? Though hindi nyo na to kailangan gawin sa MATLAB or sa Python or to what in what programming language you're using, sinote ko na siya dito by hand using Kramer's rule. Ito yung value ni M, ito yung value ni B. Right? Mukha lang siyang intimidating tingnan, pero kakalculate nyo lang naman to isa-isa, makukuha nyo yung hinahanap yung value. Okay? And we are assured that the best linear fit will be that linear function with slope given by M and intercept given by B. Kasi ito na yung sasabihin natin list linear, ano nga tawag? Linear least squares fit para dun sa given data. And this is used kung alam natin almost may linear trend yung data. Okay. So let's look at a specific example, example 5.1. So given tayo ng empirical data, we'll look at it in table 5.1. Tapos sabi rito, tingnan natin kung ang linear fit ba is a good approach by looking at a visual inspection with the data. All right. And then after we developed we found the linear least squares fit, i-compute daw natin yung root mean square error. Yung root mean square error ay given by R. So you can think of the root mean square error to be the average absolute error. Okay? Kasi nga summation ng mga errors pero divided by 1/n. Pero tapos dahil squared yung errors, kinuha ko yung square root ng buong sum. Okay? Kaya si R, pwede yung interpret as the average error. Okay, okay, let's do this step by step. So table 5.1, ito yung given data natin. This might be brought about by an experiment or by a simulation. All right? So yan yung given data. Tapos pag pinlot ko to ay na scatter plot, ito yung itsura niya in 5.4. And you see na mukhang parang isang straight line lang to or parang linear talaga yung trend ng function. Right? So this plot will give an indication na mukhang maganda na gumamit ng linear fit para dun sa data natin. Right? So if that's the case, then we'll proceed. Computein nyo yung mga kailangan dun sa formula 5.11. Ano nga ba? Yes. Kunin nyo yung mga kailangan yung ingredients para ma-compute si M at saka si B using this empirical data. Given yung X sabay at saka Y sabay. So si N ay 21, number of points. Tapos sum ng mga X sabays ay 63. Sum ng mga X sabay squared ay 219.8. Sum ng YIs ay 9.326. Sum ng products ay 60.7302. Then I'll use this information in equation 5.11 to get M and B. Now M and B are given approximately by this guys. Yan pala dito, dinisplay ko yung value ni M at saka ni B to 6 decimal digits lang. Pero in all of my calculations, ginamit ko yung exactong value. Or ginamit ko yung maximum precision na kaya ng calculator o ng computer ko, right? Pero for sake of demonstration, pinakita ko lang yung yung parameters up to 6 decimal digits. So these are the values of M and B. So our best linear fit would be given by this function f hat, or approximately by f hat, right? Ito lang si M, ito si B. Okay. And sure enough, if we will plot f hat and the data points in one coordinate plane, ito yung makukuha ko. Ito yung least squares fit that best represents or best captures the trend of the given data. Sabi natin mukhang linear yung trend. So hanapin ko ano yung pinakamagandang line. Kasi posibleng yung line mo nandito, or pwedeng pa ganito yung line, pwedeng pa ganito. Pero itong mga red lines na to, they will not be the best fit kasi hindi niya ma-minimize yung sum ng mga errors. Or actually, yung makakapag-minimize nung error o nung sum ng squared errors ay itong function na to. And that's guaranteed by the analysis that we did earlier. Okay? Tapos ang kagandahan nga nito, ito yung model natin para dun sa data. Kung gusto mong i-approximate, ano kaya yung value kapag si x ay equal kay 6? Kung polynomial interpolation yung ginamit natin, so posibleng ganito yung itsura ng function na makukuha natin. Kaya lang posible mag-wiggle siya sa edge ng interpolatory interval kasi nga mataas yung degree. We are using 21 points, so we expect a degree 20 interpolating polynomial which might be subject to wiggles, right? Tapos ang disadvantage niya, hindi ko siya pwedeng gamitin para i-approximate yung value ng function when x is equal to 6. Kasi labas na yun ng interpolatory interval. Pero yung linear fit is designed to minimize the error and capture the trend. So pwede ko itong gamitin. Extend ko lang siya ng konti. Kasi nga, ang pinapromise niya ay i-capture yung trend. So we expect that if x is equal to 6, then if the trend holds, then yung function value ay malapit dito kapag si x ay 6. Pwede ko itong gamitin pang forecast or pag-approximate ng function value sa labas ng interpolatory or ng given data points. Hindi na nga pala ito interpolation. And you will see, hindi niya talaga in-interpolate yung given data kasi hindi siya nag-pass through dun sa given data. All right? So, any questions so far? If you'll allow me, I'll borrow 5 to 7 minutes more para lang makasabay ako dun sa kabilang section kasi natapos ko sa kabilang section yung pagpapakita na stable etong linear fit, at least for this case, with respect to small perturbation in the data. Okay? All right, so kung walang tanong, so I'll proceed. By the way, kinompute yung mga errors. Yung least squares error, kinompute nyo yung sum ng mga errors squared, makukuha nyo yung 0.616095. Pero to get a better interpretation about it, kinompute natin yung root mean square error. Ibig sabihin, ito si E, minultiply ng 1 over n, tapos kinuha yung square root. So, ibig sabihin, on the average, ang error ay 0.171283. Kaya lang medyo hindi tayo nakakakuha ng gaanong insight pag tinitingnan natin yung absolute error. So usually gusto nating makuha yung relative error. So yung relative error ay yung root mean square error divided by the square root nung 1 over n times the sum ng mga yi squared. So we can think of it as the magnitude o gaano kalaki yung ina-approximate natin na data. Kasi ito yung total error dun sa buong data set. So ito yung percentage error. Okay? And if we compute RL, or this relative root mean square error, makukuha natin ay 0.1248. Meaning on the average, the error is about 12.48%. So yun yung nakuha nating best linear fit. That might not sound to be very accurate, pero yun na yung best na makukuha natin from a linear fit. So tingnan natin kung stable nga ba itong algorithm na to, itong method na to with respect to perturbation in the given data. So dito sa example 5.2, kukunin ko yung linear fit dun sa data pero hindi ko i-assume na perfect yung data ko. I-assume ko na yung data ko ay tainted by small perturbations are sabay. It could be measurement error, it could be a simulation error, or round-off error. So what I do is to use y tildes instead of y's. How do I get y tilde? Kinuha ko yung given data from the problem, tapos dinagdagan ko lang siya ng random number. And this is a random number from from negative 0.1 to 0.1. Ibig sabihin, inisud ko lang ng konti yung y sabays. And you see in the next figure, yung plot ng original sa perturbed data. And you will see na konti lang talaga yung ginalaw ng mga data points. Okay? And then kung gusto mong i-quantify gaano kalayo yung original data mula dun sa perturbed data, pwede mong computein ito. Okay. Ano yung bibigyan niya sa atin? Ito ay sum ng mga errors squared between the given data and the perturbed data. Kunin mo yung sum ng mga squares na yon, i-divide mo by the size of the original data. So sum ng squared ng mga original data. Kunin mo yung square root, makukuha mo 0.0327. So this value can be interpreted as there is a 3.27% disparity between the original data and the perturbed data. Okay. And that is not too much, right? And I think this is fair to assume kasi usually nag-allow tayo ng margin of error na plus or minus 5% for most applications, right? So inassume natin na yung measurement error is about 5%. And this is one particular case na medyo off yung data na gagamitin ko sa paggawa ng linear fit kasi nga due to some unavoidable circumstances, all right? So, and 3% is not that much, all right? So if I will do the same thing, computing for M and B, but instead of using the y sabays, I'm going to use the y tildes. Ito yung makukuha kong least squares fit. Okay. Tapos i-plot natin si G together with the original and the perturbed data. And you will see here si G tilde, si G ay yung yellow line here. Makita nyo, it sort of still visually captures the trend of both the original and the perturbed data. Okay. Now, kung i-compute natin yung relative error using G with respect to the perturbed data, we'll get 0.1177. So meaning on the average, the least squares fit that is linear that we calculated captures the trend of the perturbed data by about with error of just around 11.77%, which is close to what we got dun sa original data, which is about 12 point something percent, right? So hindi sila ganun nagkakalayo kahit na tainted by 3% noise yung ating data set. Okay? Further analysis is pwede kong computein yung relative error with respect to the given data. So si y sabay yung given, siya yung original data points. Pag dun ko kinompare yung model natin na si G hat, tapos kinuha ko yung relative error ay 12.51%, which is very close to the relative error that we got with F hat. Kasi si F hat, tingnan nga natin. Ang error kay F hat ay, ang relative error ay 12.48% gamit si F hat. Tapos ginamit na natin doon yung perfect data. Pero dito kay G hat, gumamit tayo ng erroneous data or perturbed data. Pero yung error with respect to the actual data ay 12.51% lang. So, konting-konti yung pinagbago, right? 3.27% yung measurement noise, pero magkalapit pa rin yung relative error, right? So that means medyo stable yung least squares approximation with respect to perturbation in the data. And then, if you are more visual, pwede natin i-compare ano yung nakuha kong linear fit gamit yung original data saka yung perturbed data. In figure 5.8, makikita natin yung dalawang models natin para dun sa data side by side. Now, they almost overlap. Pero kung makita nyo, meron lang, nagkakaiba sila, may pagkakaiba, pero hindi ganon kalaki. Right? And to further support this numerical, this visual aid, na okay, kahit pag inisod ko ng konti yung data points, hindi nagbago ng masyadong malaki yung nakuha kong model para dun sa data. So if you want to convince really your reader, aside from providing just a visual evidence, pwede mong i-compute yung relative difference between the two models that we got. Si F yung gamit yung original data, si G hat yung gamit yung perturbed data. Let's get the L2 relative error. So remember, ito yung L2 norm ng function. So compute lang natin yung yung mga absolute values dapat nasa loob. Okay. Compute lang natin itong mga integrals na to. Ito yung L2 norm na dinefine natin when we talk about Legendre polynomials. So ibig sabihin, on the average, ito lang yung relative difference ni F at saka ni G. So that means meron lang about 0.93% kasi relative error to eh. So you can think of it as a percent error. So there's only a 0.93% difference between the two models, even if the data we use to generate them has difference 3.27%. So yung 3.27% na difference between the data set ay nakapag-produce lamang ng 0.93% na change dun sa dalawang models. Ibig sabihin, hindi ganun kalaki yung epekto ng small perturbations in the data in the models that we will get. And hence, we can say that this is an indication na stable yung curve fitting, yung linear curve fitting with respect to perturbations in the data. Right? Kaya lang medyo ano to isa lang tong specific example. Kasi si G hat, nakuha ko by adding a random number to the actual data. So if you want to convince your reader, you might need to perform the same experiment multiple times by doing the randomization again multiple times para makakuha ka ng maraming mga G hats para ma-convince talaga yung reader na okay, kahit ilang beses kung randomly i-move yung mga data, hindi gaano kalaki nagbabago yung model na nakukuha natin. Kasi maliit yung percent difference between the model using the actual data and the perturbed data. Right? And yeah, kaya sinasabi ko, ini-stress ko na ito ay indication lamang. Hindi to actual proof. Kasi yung actual proof ng stability, dapat ipakita ko na kahit anong perturbation doon sa data points, dapat maliit lang yung percent difference. Kaya lang baka naging, dito sa example natin, baka naging maswerte lang ako na yung nagamit kong random numbers produced good results. Pero trust me, when I did the simulations, nag-run ako ng multiple experiments, siguro mga 10 or 15 simulations, randomization, na laging maliit lang yung relative error ko nakukuha. Kaya masasabi ko na this is an indication or this is a suggestion na stable yung algorithm. Hindi katulad ng polynomial interpolation kanina para kay sine of 2 pi x na nakakuha ko ng isang randomly perturbed set of data na nagbigay sa akin ng malaking change dun sa nakuha kong model. Right? So yon. So ito yung linear least squares fit. So next time we'll be talking about quadratic least squares approximation, but the derivation is similar to how we did the linear how we found the linear least squares fit. So tingnan natin siya next time. All right? So sorry, overtime na. So any questions, guys? So if there are none, then that's it for today. I hope you guys enjoy the rest of the day. And let's see each other again on Friday. Oh, by the way, ang coverage ng problem set 1 ay hanggang sa matatapos natin sa Friday. Okay? Kaya bibigay ko na siya talaga kagad ng Monday para masimulan nyo na siya. You have more days to finish it. All right? Okay, that's it for now. Bye, guys.